and a half.
Oh, wow. Okay.
So yeah, so are you guys all ready?
Oh, yeah.
Yes,
Yep, they're ready.
All righty then.
ready to go.
You go for it.
All right. Yes, we're recording. But thanks for checking. So I'm Rory. I'm the project lead for the University of Minnesota Rocket Team. And this is Gavin.
I'm Gavin, the president of the University of Minnesota Rocket Team.
And this is our safety review. So don't have an agenda really, but we'll just be going over a brief overview of the rocket and where we're standing in terms of the flight profile and the ConOps, and then break it down subsystem by subsystem along the entire rocket. And then we'll have some time for some questions.
Very good.
At any points, if there's anything you'd like to address. So our rocket North Star is a 30K SRAD rocket with a solid motor. It is 162 inches long and 143.5 pounds wet mass. It is a dual deploy rocket, so we'll have a drogue parachute that deploys at apogee and then main parachute at 1,500 feet. In terms of internals for the rocket, we have a pitot-static tube, air data sensor at the top of the rocket. Inside the nose cone, we have our SRAD universal flight computer and our team's SDL payload. The main separation point is in between the nose cone and the upper body tube. In our upper body tube, we have our main parachute and its harness. The coupler between our two body tubes houses our recovery deployment avionics. And then in our carbon fiber booster tube is the drogue parachute and its harness and our SRAD-O motor. And we also have carbon fiber fins, 4 fins. In terms of the ConOps for the rocket, it follows a pretty standard flight profile. Our motor burn will be 8.4 seconds. It will burn at around 9,000 feet above ground level. We'll have drogue deployment at apogee. That should descend us at around 75 to 100 feet per second, depending on where we are, between main deployment and apogee. Then at main, 1,500 feet, we should touch down around 22.5 feet per second back on the Spaceport America desert. In terms of our simulation values, for the height of the rocket is 162 inches. We have 1/8 body tubes, so that puts us at a 6.25-inch outer diameter. This number is a little bit outdated. We removed some ballast, but our wet mass with the ballast is 153.5 pounds. Dry mass would be 114.2. We have an SRAD-O motor, which we'll talk about in a little bit, with an average thrust of 4,652 newtons. Our predicted apogee is 30,055 feet. We have a main descent velocity of 22.5 feet per second, and we're using the standard 17-foot rail length from Ezra. Our liftoff thrust to weight ratio is 8:1. The off-rail velocity, depending on the sim, is 83 to 86 feet per second. We have a max acceleration of 9 Gs on ascent, and we hit a max velocity of Mach 1.4. That occurs just before motor burnout as it's sort of trickling down. And for the flutter onto the fins, we have a safety factor of 1.7. I'm not sure what the divergent safety factor is, but it's more like 3 or something. So we're more concerned about the flutter, but we have a pretty decent safety factor to work with there. In terms of the sims, this is something we've been concerned about due to a relatively low off-the-rail speed, at least for what the competition suggests, and some stability concerns. So we decided to prepare a variety of simulations with various ballast or aerodynamic surfaces attached to work on controlling that stability and apogee. In the first column is what it would look like with no ballast currently, where even with 15-mile-an-hour wind speeds, we'd be looking at 31,500 feet apogee, which is a decent bit higher than we'd like, and a 1.5 minimum stability, 5.73 maximum stability. So we're more curious in either adding additional ballast or adding some aerodynamic surfaces. One thing that has been suggested is adding external camera mounts, camera shrouds to the outside of the rocket to get, control that altitude and also get some nice footage while we're at it. That brings us much closer to the target 30,000 feet apogee for the variety of wind speeds, while also generally holding a better stability profile. This 15 mile an hour with the 10 pounds of ballast is less stable than we'd like. So we'd probably, look at either adjusting where that ballast is applied or controlling other means. Our flight last year had a very similar rocket in terms of the overall scope. But when we flew it, it was very windy. It was. Were you there at SA Cup last year? Okay, no. This was the second launch day, and when we launched, I don't know what wind speeds we're clocking in at, but it must have been between like 12 to 20 miles an hour, depending on the gust.
The remote. You go ahead. Sorry. I was
Oh,
talking to
it's okay. But using a very similar motor
side.
that we restatic fired, we were able to achieve a very nominal flight profile with a small flight path angle and good stability throughout. In terms of the sub-teams that work on our rocket, we divide our work into 7 sub-teams, and we'll focus on some of those physical ones right now. So starting with the airframe of the rocket, we have a fiberglass upper body tube, which is 1/8 inch thick, 4 feet long, 48 inches. It's manufactured in-house, an SRAD fiberglass tube made with biaxial woven sleeves, laminated with air epoxy 2036, and I can't remember what the hardener is. It's 3060. Yeah. And then our booster is also SRAD, but it's carbon fiber. Same thickness, 69 inches long, so that's almost 6 feet. And same biaxial sleeves, just carbon fiber. We also use a variety of sleeve diameters to achieve a more quasi-isentropic stress relationship to withstand various different angles of attack. Our nose cone is a Wildman COTS nose cone, 5-to-1 bond Karman, and we modify it because its OD is I think it's like 16th inch thickness for the bottom off the shelf. So we add a few rings of fiberglass sleeves to bring it to the same outer diameter as the upper body tube. And atop that nose cone, it's not shown in the picture, but we have our pitot-static tube. We also have carbon fiber fins, which we have. The next slide will be dedicated to those. And the fiberglass coupler is COTS Wildman, 6 inches length to each side of the connection, and 9 inches for the nose cone one, just to house the payload. For those fins, it's a trapezoidal profile. They're 0.33 inches thick. We vacuum bag our fins. They're also SRAD, using quasi-isotropic carbon plates and air epoxy for the laminating. The fillets that we apply are done using rocket epoxy, and we also apply 3 layers of carbon tip-to-tips with the air epoxy for increased strength. The flutter and divergence velocities are both in excess of Mach 2.4, which yields that safety factor of 1.7. And those are also the fin dimensions in the figure on the left. For our propulsion system, our SRAD motor is named Charlotte. It's a 6-inch motor, 90% O, and we static fired it in February to validate those numbers. That's 39.3 pounds of propellant, 38.6 pounds of hardware. It reaches a peak pressure of 800 psi, and it burns for 8.4 seconds. The thrust curve is in the figure on the left. This is a video of our static fire. And 5, 4, 3, 2, 1, ignition.
How long is your motor?
Our motor is 1,079 millimeters long. I know it's the ENG file. I think that equates to around 40 inches. Andrew, if you've got the number on hand.
Yeah, the motor is 45.8 inches.
45.8. Okay, a little bit more than I said.
That's a monster.
Yeah. Experienced a nominal burn. It was lovely to see work successfully, and we intend on having just a successful burn on the actual flight. For the hardware, it's fully aluminum with fully SRAD made in-house hardware. Our forward closure assembly has a pressure transducer to collect pressure data during flight, just for more validation. We use just a COTS easy motor pressure transducer, and that routes to our AV bay for data collection. We have a bolted retainer design with 12 half 13 low profile bolts, for their bearing surface area and, increased shear. The nozzle assembly has both phenolic and graphite nozzle sections, also affixed by bolts, and there are dual redundant O-rings on both closures for containing the gases. Andrew, you want to take this slide?
Yeah, so I'm Andrew, I'm the prop lead. These are some extra things I just want to mention. For our igniter, we use a potassium perchlorate boron nitrocellulose dipped E-match in the bottom left image. And then we use 2 of those and wrap them in Blue Thunder, and that's what we use for the ignition. We use this both in 2021, 2023, and also that static fire. We also were able to CT scan our grains to kind of to validate how well we casted them, and those are the images right there.
So we observed very little voiding in the grains for that static fire, which helped it perform so nominally, and we were performing the same analysis for our flight grains. For the parachutes on the rocket, we use a disc gap band drogue design and an extended skirt main design. Our disc gap band is a design we've used for multiple years, based off of NASA's work with the Viking program, and it's been very successful for us. We want something with a little bit more drag benefits for the main, so we switched to an extended skirt design this year, which we have flown multiple times to good success. It's a 5.5 foot diameter for the drogue and 20 foot diameter for the main. For the harness, we do extensive testing and validation to make sure that our harness will be able to sufficiently take the loads placed on it during the recovery deployment. Our weak link is these 3/8 inch steel U-bolts that are attached to the avionics bay, which at 5,375 pounds braking. If we look at the shock force calculations in the bottom right, is a safety factor of about 3. So we're pretty confident in those. For the deployment of our recovery systems, we have 5 632 nylon shear pins that attach the upper body tube to the nose cone and the booster tube to the coupler section. At their minimum manufacturing braking strength, they provide like 76 pounds each, so that comes out to 384 pounds force minimum braking. The main factors we're concerned about for breaking them prematurely is due to drag separation, which from our Ross arrow calculations comes out to around 105 pounds differential at max. So a 3.6 safety factor, which again, we're not particularly concerned about. And then potentially breaking the upper body tube to nose cone shear pins at drogue deployment, which I know you've had some concern about with other teams in terms of popping main at apogee. And we can discuss that if you'd like. But we have a variety of calculations to believe that this should be a sufficient strength for taking those forces.
I was more concerned about the length of your recovery harness. When it came to that, I would rather see less beefy shear pins on the drogue side, so that there's not and the length of the recovery harness is to keep it from jerking really hard at apogee.
Yes.
And shearing the other shear.
Yes.
So
and
we can talk about that.
Okay. Yeah. We also daisy chain our shock cords to distribute that peak shock force further, so that just as it's unfurling, it's sort of dissipating some of that internally. But we can definitely look at reassessing the sizing on those drogue shear pins. Our ejection charge. Sorry.
It looks like you're go back to that other picture, please.
Okay.
That one. So on your drogue, it looks like it's 25 and 35. That looks like it's plenty.
The harness length?
Yeah.
Yeah, 15 and 35 plus this additional 10, I think is what. Yeah. So that brings us to a total of 60 feet on the drogue harness and then 70 feet on the main harness.
And we increased that value after your suggestion from the
Second progress.
second progress
Yeah.
report. Yeah.
That looks good to you then?
Yeah.
Okay, great.
Yes. I haven't seen anything I don't like yet.
Love to hear that. Our primary ejection charge sizings for our drogue and main are 12 grams and 18 grams respectively. And this is a video of our successful main ejection charge testing. Quality is not great. In terms of recovery avionics, we have dual redundant flight computers. So our primary is an AIM Extra, which has a pyro battery and a computer battery. The Telemega, which is our secondary, and those are both GPS flight computers. And then a Easy Mini Tertiary, which will use barometric pressure, all controlling ejection charges. The AIM has lithium ion batteries as per competition requirements and regulations, while the Altus Metrum products both use supplier offered LiFePO batteries.
Mhm.
And we've done battery testing on all of those. I think we submitted that with the second progress report as well. Yes. Third progress report. There we go. Our payload is a scientific payload, a DIH system, which stands for digital inline holography. It's an airborne particulate measurement system, which will measure particles in the air during our ascent and descent of our rocket. It uses DIH and an optical dust sensor for redundancy in the collection, because we've never done this before, so we're kind of interested and curious to see how our data quality looks really. And it remains rigidly secured within the nose cone for all of flight and recovery. So no deployments, no mechanical systems. And then the other two components on our rocket is our universal flight computer, which is purely for data collection analysis. It doesn't control any deployment charges. It's a modular flight computer that we hope to be able to fly on a variety of rockets, with each card having a specialized function that can be swapped out for the given rocket or flight's requirements. It also uses lithium ion batteries, and the payload does earlier, forgot to mention that. And then at the top of the rocket is our 5-hole PSS, which will take data for the angle of attack and angle of side slip of the rocket alongside the static pressure. And we'll feed that data into the UFC for collection and analysis. And that's pretty much what we've got. We have the rocket sort of disassembled here, if we'd like to look at any components. And otherwise, if you have any questions, we'd love to answer them.
I'd like to see the rocket.
Yes.
All right.
So
Do you
Gavin will
want
walk you
to-
through it.
Direct your attention to the Rory Conway's video. And then do you want to talk to Rory, and I'll just.
Yeah, sure. So these are our body tubes, manufactured and painted in-house. Pretty happy with how those turned out. 69-inch body, lower body, and 48-inch upper body. Pretty straightforward. We have a 2-inch switch band on our coupler down there, and 6 inches of coupler length on each side. There's that monster of a motor you were talking about earlier. Yeah, it's a big one. And then there are also the rear and forward closure assemblies disassembled.
Can I see, well, yeah, that,
This?
what is that on top? Is that the forward closure?
Yes.
Yes. So that's the pressure transducer.
Oh, gotcha.
Yes. And then those two other holes are for eye bolts for the recovery retention.
Gotcha.
Yes.
So what is your motor retention?
Our motor retention is after tension. It's just bolted through the bottom of the booster tube. Yeah, those bolts that Gavin's gesturing to. You can also see them on the booster. That's kind of all the way down there, but yes, rear retention bolted.
Okay.
We have a testing report on the pullout strength of those bolts. And we see a factor of safety of, I believe, 12.
Yeah, what I'd like to see is when it's when it's fully assembled, do those bolts stick out?
No, they
Okay.
are
They're
countersunk into the body tube. I'll get up close to it right here, so they do not stick out.
Okay, perfect.
I guess one exception to that is that our rear
Oh.
rail button is one of those bolts.
Yes.
Just for convenience.
Well, that's,
Yeah.
I mean, that's supposed to stick out.
Yeah, it better.
I just prefer not to see studs all over your
Yeah,
all over the outside surface of your rocket.
yeah, right. These are,
So,
okay. Yeah.
here's our Av Bay.
Yep.
Uh-huh.
And then here's our nose cone recovery connection. So this is our H block. See, these are steel roll pins that are epoxied in and then will be cut off to make
Oh,
this
okay.
shape. They just need to be sawed off.
Okay.
Then we have our nose cone, with currently the PO2 isn't on it, so we have it disassembled for showing off.
Oh, my.
Yeah. So this is fully manufactured in-house, and we characterize its performance at Collins Aerospace's transonic wind tunnel, a few miles out of the cities. It's really awesome. We did our podium presentation on it last year, and we're just going to keep flying them because they provide some really good data.
Very cool.
Yeah, here's the universal flight computer with some temporary bulkheads. They're MDF right now. We'll end up cutting them out of fiberglass. This is just for test fitting components. But it's a full stack. The cards are currently not in it right now because I'm pretty sure our avionics team is working on them. They always are. It is really impressive, and we're really hoping to get some good data from it this year. And this is the externals of the payload system, a 3U CubeSat form factor. Yeah,
That will be housed in the nose cone.
yes.
And how much does that weigh?
8.8 pounds, I believe.
Ah,
4 kilograms.
Yeah.
It will weigh what it needs to weigh for the competition.
Exactly. All right. So I think that pretty much concludes our presentation. So if you have any questions, we'd love to answer them. Otherwise, I think we have a few questions in the house that you may help us with. So we did have a question about weigh-in for payload in 2022 that occurred like morning of Wednesday for the first launch date. Although last year we were able to do it at, I think it was the conference day, or was it check-in?
It was conference
day. So we were wondering if you had any insight on when that would be open to us, because then we'd be able to do that the night beforehand.
no, but it might not be a bad idea to post it on HeroX
Okay.
and have Andy answer that. Since they haven't really kept me up to date on things like that. So yeah, it would be worth finding out.
Okay, yeah. Thank you. And then the other one was last year the waiver altitude was 35,000 feet. I don't know if you know this, we could potentially reach out to Ken, the RSO for it as well. But we did hear that the waiver altitude could have been increased to 40,000 feet this year. Do you have any news on that potentially?
I had not heard that it had been increased.
Okay. Okay. Does anyone else have any other questions? Any inspiration striking them now? All right. Yeah.
Oh, can I see your parachute and your recovery
Yeah.
harness?
Yeah. We got those separated. Whoops. They're a bit sooty from ejection first testing earlier this year. This is our main parachute in an S-thread deployment bag. It's made out of fire resistant Nomex. With currently Kevlar suspension lines.
Uh-huh.
And then we have our dynamo recovery harness that uses soft shackles instead of quick links.
Yeah, I'm sorry, it uses what?
Soft shackles instead of quick links for weight reduction.
Okay.
So our parachutes are made out of 1.1 ounce whipstop nylon, and then this year we pre-dyed some of the fabric to make it visually distinct in the sky.
Uh-huh. So I can't really tell from here, from a video, but how many times have they flown, and do you check them before prepping them to check them for holes and things?
So we've only ejection charge tested our parachutes, so that's why they're a bit dirty, but our parachutes have not flown in any other rocket before we make them custom for each SA Cup rocket.
Okay. And were you able to do any sort of test flight?
Yes, we have done multiple subscale test flights on the same parachute geometry. I believe we've blown it probably about 5 times at this point.
Mm-hmm. And where do you fly?
We go and fly up in North Branch, Minnesota, so
With Tripoli, Minnesota.
yeah.
Oh, okay. Is that your prefecture, Gary?
Yes, it is, Elaine. Yeah. It's about 30 miles north of the cities here. So it's and it's on a sod farm, so it's a beautiful place to
Oh,
fly, actually.
nice.
Yep.
So you can basically fly all year.
Yes. Well, yeah, I mean, we do fly in the winter occasionally. It's a little cold up here, but
Well, yeah.
we could fly.
Well, and I'm in Virginia, so
Sure.
we have times in the winter where we can't fly because it's just plain too wet.
Oh, yeah. All right. Well, that
And
makes sense.
so we do occasionally get, some really cold winters
Mhm.
where, and it's so damp that it's just not safe to be out there when it's less than 32.
Sure. Sure.
And no offense to the students in the room, but they don't tend to dress for the weather.
Well, we've taken care of that. You guys are really good at that. So that's great. And this year we were lucky; we had very little snow, so we were even like the video of the motor tests. I forget what was that, February? I can't remember. March, whatever. Anyway, whenever we really had very little snow this year, so it was a really good winter for flying for us.
Nice, very nice. So, I think you guys are in pretty good shape for the competition. This is probably the shortest safety review I've done. You presented all your data in tables so I could read it easily.
Yeah. We make an effort for it.
Well, I appreciate that. Since I'm likely to get your team again next year, I appreciate it. And next year, I'm planning on going.
Oh, wonderful. You won't be there this year then?
No, I'm afraid not. You might have my husband Ben as your safety reviewer.
Okay, yeah.
He's standing in for me with my team as
We
well.
did him last year.
Yeah, he was a reviewer.
So it's well, no, it's unfortunate you can't make it this year, but we'd love to see you next year, Elaine.
Yeah, well, last year I changed jobs, so I had no vacation time. I
all right.
just changed jobs. So, and this year, I had the knee surgery, and I used up all my vacation time in the 2 weeks I took off.
Sure.
So, yeah, it was just like that.
Yeah, understand.
Hopefully we'll have another good rocket next year as well to show off, but so then we'll see how this one flies.
Yeah.
Yeah, thank you so much. It's been great. And we'll work on getting this video up to Ezra pretty soon and keep working towards the actual competition. Thanks for your help throughout the whole process.
Well, if you have any questions further before the contest, just send me an email.
Great. Yeah, thank you.
Oh, you're welcome. And don't forget, plenty of water,
Yep.
lots of bathing sunscreen,
Mhm.
a wide-brimmed hat, long sleeve fishing shirts, long sleeve SPF 50 pants, and hiking boots or work boots. No sneakers or flip-flops out in the desert.
Yeah, we'll try and catch that from anyone on our team before. Yeah.
The last time I was there would have been 2022, and I had a big long sleeve fishing shirt and I had to give it to somebody. I don't even remember what team they were on, but I had to give it to somebody because they were not prepared, and they were on the first day they were bright red. I mean, like couple hours after we were able to start flying, they were red, and I was afraid they were going to spend their week in the medical tent.
Yeah, I make sure that anyone going out is properly dressed, and if they're not, they're staying at the hotel. So
Yeah.
they know.
And I'm happy to see that your rocket is not painted black.
Yeah.
Um,
We've been going to the competition for around a decade now as a team,
Yeah.
for his SA Cup. And in some of the old photos you see, black rocket, tank tops. We know better now, hopefully.
That's good. That's good. Yeah, the hybrid teams just never seem to learn. They're the ones that paint. They have to keep their liquids cool, or their gas cool. And Cat, excuse me.
Wants to be a part of it.
Yes, he photobombs everything. Go ahead, get down. You big old baby. So, yeah, black rockets, not a good idea.
Yeah. Too aesthetically pleasing for their own good.
Anyway,
Yeah. Yeah, thank you.
you're very welcome.
Yeah.
You were very well prepared for this. You
Yeah,
made my day.
we put a lot of effort in the last couple weeks into being ready for this, so glad it paid off.
You did.
All right, thank you, Elaine. I'll reach
You're
out
very
if
welcome.
you have any other questions. Bye.
Gary, do you have any questions?
I do not. I think, yeah, I don't know. I've been going there ever since it started. I think up and before that in Utah. So I'm good, I think. So I've had a few conversations with Ken, but about different things. So got those questions answered
Very good.
around batteries and waivers and that kind of stuff. So
Okay, cool.
yeah.
And you, I don't have to ask you about your experience as a level 3, I'm sure. And are you experienced enough to be a flyer of record?
Yeah. I am.
I know. Alrighty, guys. You have a good evening. And you
All
can
right,
stop
you too,
recording now.
Elaine. All right, say hi to Ben.
I will do that.
All right, take
Bye-bye.
care. Bye now.
Bye. Bye.